G'day guys, and microphone around that way, might be able to hear me. Okay, been working on this SD2200, putting in the variable frequency, new front end, variable gain, and just optimizing the detector in general. And one thing, I found this probably on numerous occasions, and I should have made mention of it before because it probably has an effect on all these older detectors. And I'm going to show you basically, I've shortened, you can see here the cable here. I've put on a powdered iron choke. I've got rid of the ferrite, which had multiple turns around it. It actually affects the sensitivity of these detectors. So iron cores are good because they don't saturate by getting whacked with a mono pulse. We'll show just a standard square wave, one polarity pulse repetition. Ferrites, if they're not sized right, do not like that at all. There's no reset mechanism in a ferrite, whereas the iron cores have a integral air gap and they don't suffer any saturation. You can actually cause interference by using the wrong type of ferrite. If it saturates and goes non-linear, it can cause interference. Anyway, this is probably more important. So this is the litz wire they use on the transmit side. So I've just chopped it and shortened it. So there's a couple of bits of that. And you've got to remember the patents for this. There's the input wire, and there's a yellow one somewhere, which was the ground. Well, the low noise ground wire, wherever it's gone. I don't know, it's probably on the floor. I don't know where it's gone. But anyway, we can, oh, see my hand, silly me. Jeez. I'm twiddling something in my hand. I don't know, where's the wire? It's right there. Dear me. Anyway, remember about all the information about cross-sectional eddy currents, and there was patents to address this because it was all to do with the stranding of the wire generating eddy currents, and that's why the big song and dance. I just want to turn that meter off because I just noticed it was on. All the song and dance about litz wire, multi-stranded insulated wire. Well, what I thought was interesting is that we got litz wire coming in on this detector here, well, to the coil, and it's just as critical on the receive wires as the transmit wires, because you can set up cross-sectional eddy currents with low-level signals or high level pulses. Doesn't make any difference. It still does the same thing. So here we go. Let's have a look. This blue wire here, the blue wire is connected. Is basically that long, including where it connects here, wrapped around the core, and goes to the circuit board. So I said, oh, okay, well, let's have a look and see. Well, there's me thinking, if it's not litz wire, it must be multi-stranded wire, but tin plated. Each strand is tin plated. That actually helps burn off the cross-sectional eddy currents. And you can read up specifications on the old patents on this thing, and it had to have a strand diameter of under 1.2 or 0.12 millimeters, whatever it was all worked out. And we'll have a look at this, okay? So I'll just get this and I'll strip that off. Okay, so I'm thinking, well, that's a bit bigger than normal. That's probably getting onto about 0.5 millimeter. So that'll generate, if that was a single wire, that would generate eddy currents. And if it came into the receive window, it would cause a bit of problem in the receiver, noisy receiver. So here it is here, and I'm saying to myself, put that over there. We'll get this meter. I like this meter because it beeps. So put it on diode range. So, and if we go across the strands, if that was litz wire, there'd be nothing. And, oh no, it's not litz wire. It's not tin plated. It's just copper strands, right? So they're all touching each other, and it might as well be one big hunk of copper, right? With litz wire, if I got the litz wire here, and I'll just peel it like so, I'll take off some of the insulation. It's a polyamide insulation. I'll chop that here. It's been soldered, but yeah, it's been soldered. It's actually stuck a little bit. Okay, well, I've ripped off the insulation on the litz wire. Normally they used to cover this with silk, but that would be a bit crazy these days when we can use synthetics. So if I get this litz wire and put it across the strands, well, look at that. They're all insulated, aren't they? There is no continuity. And that's how it's meant to work. Like I say, it's amazing that it was a big thing about litz wire in coils. Basically, the coil cables are made the same, but it's the last percentage in the detectors, not litz wire, is it, on the receive? So there we go. That is, you can see it's got varnish on it. It is litz wire. And yeah, the actual receiver input wire is not. You can hear that beeping away, or you can see on the meter it's just dead short circuit. So there's me thinking, oh, well, I'll trim these up and I'll do it a different way. Well, actually, what I've got to do now is undo all that work, and I have to replace the wire completely from here to the board, and yeah, make sure I use either some tin plated copper wire, or I use some smaller gauge litz wire. I'll just use tin plated copper wire. There's not that much of it, and actually over a small length, it doesn't, in just about all cases, it's undetectable. Which means it's not seen by the circuitry and causing any sort of issue, basically desensitizing the input stage, because that is what it will do. Depends how fast you clock these things, by the way. These are clocked fairly slow, but you know, we put variable frequency on it, so if it clocks up faster, there may be an issue. So it has to be loose stranded, tin plated, or litz wire. I just thought I would point that out, just because, yeah, just because I looked at the wire after I trimmed it, I went, it looks like straight copper, and it is. You know, over that length there, maybe it doesn't, but when it was wrapped two times round inside that ferrite, that could actually increase the issue with that size of the wire, how reactive it is. But like I say, technically, you know, like I say, the big hullabaloo about using litz wire in coils to get greater efficiency overall, less loss, and then, you know, the final part of it. You know, I was going to say something as like the Chinese would do. You know, this is like 95% right, not quite, but you know, it is what it is. Maybe they didn't realise it was just normal copper, and maybe it didn't make any difference. But let's be politically correct here. You know, the patents say this, that, and the other, and they do it as per the patents. For the coils, they do it for the coil cable. And that's just an extension of the coil cable. So we just say, well, we have it that long, we're not going to worry about it. I don't know about that. Just my opinion, but it's factual, and I'm pointing it out for educational purposes. If you want, you have one of these detectors. Maybe you have an SD2100 or 22 or even a 2000. Maybe you want to check the wires to see if they are tin-plated, single-stranded wire, or if it's just a big lump of copper. Each copper strand just touching each other just causes the big lump of copper. It doesn't act as single little strands anymore, just for flexibility, of course. But electrically, it looks like a big chunk of copper. So, does it have an effect? I don't know. I'd have to go and do it. Well, because I've stuffed it now, haven't I? I can't go and, well, I could probably get some copper wire and then non-copper wire, and I could hook it all up, and I could look at the noise and just do some testing on the input to see how low down signal strength we can get, to see if it actually gets swamped by any generated eddy currents. But play it safe, just redo it with the what's meant to be the correct stuff. Don't continue all that good work in the coil, in the cable, and then blur at the last part of it. So, like I say, it is interesting. And also, guys, I tell you right now, even though these are what we classify as a movement detector, you've got to move the thing for it to produce a signal with a target. If you do blobby solder on the connections, big blobs, and tin up the wires, that is going to act as a piece of metal there, but it will generate the die-off eddy currents because you've created a huge lump of metal. The idea is very thin tracks, very small tracks, not small enough to become crazy, inductors on the board or anything like that. There is ways of minimizing that too if you want to go for a triple strip type circuit board layout. It gets rid of inductance and also minimizes capacitance too. So yeah, basically don't make big blobby solder connections, especially if you've got a very high frequency detector. The faster it turns on with the receive to the transmit flyback pulse, the more likely you're going to have things in there just getting charged up with energy, and they can't get rid of the energy quick enough. It's still decaying into the receive time. So very, very light on the solder and no big blobs, and just keep everything thin and narrow. Yeah, it should be right. The other thing too, if you're using a normal iron to tin this stuff, you have to burn down the varnish. And what happens is the varnish all joins together, and the wires, instead of being flexible like that, it's like trying to bend steel. So you're better off getting a solder bath or something of that nature. Get it damn well hot as, and just have flux floating on top, and like it's a little solder pot type thing, and just dip the tip in and just 1, 2, 3 done, and just make sure that the whole face, every strand has been hit with solder. Otherwise you'll have strands in there doing nothing. They won't be carrying any current. So possibly on the last part of this, you probably could just do the whole lot with tin plated wire, roughly 1 millimeter square type stuff on the transmit, and about maybe 0.25 square millimeters on the receive. It's not critical on the receive. There's really no appreciable current going into the detector. It's probably, I don't know, 20 milliamps or something maybe. It's not a lot, but you still don't want to add series resistance and have resistive losses. Not that it's much. I'm just being pedantic and being on point of, what should do what. Does it make a difference? You may not notice it, but if it did make a difference, you don't want to know that it's making a difference when you don't know, and you're going over targets and you can't hear them. So play it safe, do it properly in the first place. So looking at that, there's not a lot of times I get into these detectors and chop this off. On this one, I'm doing it because I did have a look, and it is lossy. It's easy to do. All you do is put the core with the winding through a signal generator, and just measure the amplitude of the signal in and out, and at various frequencies, either at your transmission frequency, or if you want to get really clever and try and work out the decay time of targets, you do not want to have any interaction over those time domains, and have signals diminished in amplitude, or rolled off, or completely not there. So that's one of the reasons that a lot of these detectors, I go for powdered iron type cores. The reason being too is because you're trying to, with the ground balance circuits on these, well, you'd say, well, we want to get rid of the ground. The ground's a lot of iron in the ground. It gives it a particular decay rate. Or if you look at the detector, it's a decay curve. And then you go and throw a big chunk of ferrite in it as well. It's, I don't know, it's like you make a martini and you pour in some tomato sauce. It's not very good. Keep everything the same. You're dealing with a lot of iron. Well, use iron-based chokes in your line as well. And it's you're getting very similar overall frequency decay attributes and cut off, and it's much the same. It's much the same as the ground. So I don't know why you'd want to try and tune out two things. One which is ferrite, which is totally different to the ground, and then have a quasi in the middle type ground balance response. That's my take on it. That's my opinion, right? So, you don't want to try and tune out the ferrite when you're trying to tune out the ground. That is my take on it. I'm being pedantic. I'm absolutely, nitpicking the living hell out of it, but that's what I'm doing. So yeah, you can make up little bridges and things off your frequency generator, and just have a wire where you can just push it in, push it out, and put different ferrites on there, or different chokes. Put 1 turn, 2 turns, try it, and have a look on your oscilloscope at the reduction of signal. And you will be amazed. If you've got a spectrum analyzer, that's probably even better. But you can do it on your oscilloscope. It will show, especially a very high fast one like this, will show what it is doing to your waveform in your passband, where you don't want any attenuation if you can get away from it. And all you really need to do is making sure that these chokes are doing the job of suppressing anything that's coming out, which is multiple harmonics of the switching. The hard turn off generates harmonics. They got a little tiny, I don't know if you can see, that's a little tiny choke there, which it's probably 1 microhenry or so. I don't know what it is, but that is there to slow down or basically reduce the slew rate of the turn off. So it gives it a bit of a rounded falling edge. It doesn't generate sharp harmonics. Well, that's the idea of it anyway, right? There's, it probably works. Does this work? Yes. There's probably, tell you the truth, in the whole design, there's probably enough cable capacitance to the coil to really reduce any spurious harmonics. That will also round off very, very sharp, fast waveforms and reduce any sort of generation of harmonics. The coil's a dummy load to harmonics. It's It's basically we can't call it a high frequency antenna. Uh, it falls off very quickly in what it can actually transmit any which way. It's a closed loop. It's these things that they are an unintentional radiator, and they're magnetic. They don't generate radio waves as per se. It doesn't go for kilometres and kilometres. It usually falls off at about 100 metres and you can't detect it anymore. As you probably found running around the bush with metal detectors, you get 100, probably even 100 feet away from each other, and there's no more interference. So it's not like a radio transmitter. And if you did want to transmit radio waves off these, you need a cable coming off it or a wire coming off it, probably about three or 400 meters long or something. Because the frequency of these is so low, you'd have to have a really big long wire type antenna. You could work it out if you want to work it out, but I know it's very, very long. And if you start reducing the length of a resonant antenna to something that's intentionally generating a frequency, the efficiency goes down the bunghole. It doesn't transmit very far at all. So very interesting, isn't it? Anyway, I just thought I'd point that out, that you can do change this. But we'll see how we go, and we'll get it going. We'll give it some tests, and yeah, now I'm going to unpick all my handiwork. I'm going to do it anyway. It's the right thing to do, because this is made to be a very, very sensitive, low noise, but very, very fast detector. The other thing too, I said about these things have a 2N7000 or a what is it? It also has a possibility a ZVN2106 in here, and they essentially try and load the power supply a little bit more. It puts it right on knife edge, so it could probably blow up. And what I did here is a quick and easy one, if I can get it around. It's hanging on the battery. You can see in here, I've put a ZVN2106G in here. It's got about 10 times the current capability, but it still it's a much better device than the other thing, the smaller surface mount one. And basically all I've done, this is really easy to do, it's a rectification diode here. I've just soldered the drain tab to it, and just come off the gate and the source connection where the surface mount one was, and just put in small little jumper wires onto that. So the actual diode will act as a heatsink as well, because it's fairly chunky on the leg, and yeah, straight in on the gate and source connection, and on the middle of the transistor, I just chopped the drain, the drain out that way, and then left it on the drain tab connection, and it works really good. So you get more current capability. Just change that. You don't need to worry about the pass transistors here. There's nothing really much in it. It's mainly the positive rail being generated by the switch mode. Tends to be a little bit light on for additional circuitry, which is going to draw current. So bolster that up, and yeah. So we've got our variable frequency, and we have our variable gain, and low noise front end, and yeah, let's say it's taken a little bit of time to do this. I had to build the boards up. I didn't have any boards built up, so got in there, did that, and yeah, this one here, I've got it running on the small pulses. Actually stretched those out to 80 microseconds in length, and you can go further, but as soon as you get to 100 it's like, what do you want to pick up? Big cannonballs or something like that. It's a trade-off between pulse length and size of gold. The bigger, deeper stuff, it's probably about that. So that's what I'm sort of optimizing for. Obviously, if there's a hand of faith down there or something that's like that, it's going to ring like a bell anyway. You're not going to miss it. And there's enough energy going into the ground compared to the modern detectors. Um, I'm not going to go and say anything about the super modern ones because they're their own thing. But even on the um, GPs and GPXs, 45s and GP 3000s, all that sort of series, the small pulses are only 35 microseconds. So I've got this at 80. So it's a lot more energy going in the ground. And, uh, if you start, because these things have a fixed transmit receive window, unless we go and muck around with the timing, you can do it, but I found you don't need to. When you start looking for big, deep targets, it's better off to have a little bit more dead time because it allows you just basically powering so much of the ground as well. You're really giving it a good hard long whack. You're possibly better off allowing the ground to die off and then receive. It's just because there's so much energy there that any metallic objects of decent size are just going to ring like crazy. I did some experiments before I cut the wires off, and I was trying on tin cans and basically gold rings and that, and at 80 microsecond long, I think it's about you must be getting about 260 on the long pulse. You got to remember too, that's a long time on, and it will make things get hot. But it's everything's sort of a compromise. This is adjustable. You can adjust it back up and go back towards the 60 microsecond long small pulses that this does as standard. I think it's around about 58, 60. You can go there. You can go a little bit quicker, but longer pulses, more energy in the ground for bigger targets. Like I say, the guy wants this for doing drag coils, so big drag coils, big targets, and longer pulses, longer off time window, let the ground settle down, and you can basically cut out it reacting to small surface targets like lead shot, stuff like that. Like I say, it's also got variable gain. You can crank it right up. This will detect anything, even on zero. Well, a set on zero gain. It's not really zero gain, but all the way down, it'll still detect quite okay. And the ground noise just disappears. And getting the fringe targets, crank the gain up. Horses for courses, settings for the ground, settings for the coil. You've got to get that right. So anyway, rather than waffle on, I'm going to get this done. Yeah, damn all late now. It's 9:30 at night, so I'm going to quickly just finish it off, and I might be able to kick in another video just on the final workings of it, just so you see how good it turned out. So yeah, because someone was, who was it? Someone there in the comments on the last video, I think, saying something about SD2200. They want to see it or something or other. So you're going to see it. There it is. Anyway, I'll upload this and catch us later.